Okay. So, now we are the last step. So, we developed all the tools, second order, third order correlation function and structure function. So, what I am going to do is the following. So, I am going to show the following. So, this is my layout. So, I am going to now go through dynamics. So, write down the velocity from the Navier-Stokes equation, using that time derivative of the second order correlation function ui prime. Earlier you remember that you are doing ui, total energy or total. So, it was not a different point, it was same point, but now I am taking two different points. Now, this can be shown to be, this is why we need all this stuff. The right hand side, the nonlinear term appears that like that. Eurograd u term appears as in fact structure function. This is qii m del L del m, right, is which I derived. This was there in my old slide, and this is that stuff. So, this can be shown. Now, this is connected with the third order structure function, and that is the connection. Okay. So, this one is QIIM, with which I had done this. This is equal to this one, except factor 1 by 4, but this was 1/3 this object. So, I will just map it to that and relate some with the dissipation rate, and we are at home. Okay, now let us fill up the gaps. So, how do I write this time derivative? So, half, so d by dt of ui prime plus ui d by dt of ui prime. Yes, so it is a product rule. Now, what is d by dt of ui? It is del j uj ui, right? Yes, in del j, yeah, what? So, nonlinear term, that is a nonlinear term. This is of course pressure term and so on. So, first term is that with a minus sign, So, one term. So, I am just going to just sketch it. Okay. So, uj del j uj ui, but ui. So, this operator del j will not act on ui prime. So, I can push it inside, right, because this operator acts only on r position, not on r plus l position. Now, I am doing averages. So, averages. So, this average will come here. So, the third order correlation function has come now. Okay. Now, that I relate to third order structure function, which by the all the derivatives which I have done. Now, the second term you just follow the same step. Now, derivative with here you just follow the same steps, prime, because this will be on prime variable. So, this will be del j prime, because it is the second point, uj prime ui prime. Now, ui will go inside because this thing. So, this is uj prime ui prime ui. What about pressure? So, d by dt is this minus grad p. So, minus del I p. Now, ui prime can be pushed in because derivative acts on p, not on p prime variable. So, it is ui prime. Same thing you derive for the other one. So, they have come in pair with prime switched, and there is force as well. So, d by dt is right hand side is force Fi. So, Fi ui prime averaged half and half from there. So, plus half like that, and this is a viscous term. So, there is a ui prime nu grad square u ui average. Okay, is that fine? I mean, this how, so we write that. It is just straightforward, no problem. What about this one, pressure with ui prime? This one 0. So, for given pressure my velocity will fluctuate plus minus, it has sign. So, this goes to 0. So, pressure term does not contribute, like our earlier derivation, incompressible flows, pressure drops out, gone. Now, these two, by that logic that I can switch these derivatives, these two in fact can be connected together. I will skip this algebra, okay. So I will just write down the final step. So we can relate this prime, well, these are exactly, remember we had third order correlation function and I connected a structure function. So you follow the step, and this is 1/4 del L u prime minus u whole squared u prime minus u vector. This is this nonlinear term, okay. It is just very few steps which I have in my notes. And the second term is the half and half of force, and they are equal, Fi ui prime average. So there are two forces coming and they are equal, and the viscous term. Let us assume viscosity equal to 0. So viscous term is small in the regime of my interest, but right now let us keep viscous term. I will call it dissipation dFL. I put a minus sign here, okay, following the notation. Now this one is called Tu of L, is a nonlinear transfer term, and this is coming as force L, and this is a du of L. So this is how I connected the second order correlation time derivative with the nonlinear transfer term. This is that S, you may call SUU KPQ. So this is what is exactly similar to what we did for Fourier transforms. Now we are almost there, so we will make some assumptions and connect these two, okay. So I make one more step. So these are in fact function of vector L. Since it is isotropic, it becomes function of L only, magnitude L. So that is my next slide. So this is magnitude L. So instead of writing vector L, I just write L. Now the next step, let us make assumptions. So same assumption like before, we make viscosity tending to 0, okay. So we are making the flow very turbulent, but we have very strong, very large inertial range. So I have forcing somewhere here and I have L here. Well, forcing is large scale, no? So we are looking in space. So if L is increasing, I have L here, and viscosity is very small L. These I force I have to flip it, because with Fourier space I force at small k, but I am forcing at very large scale. Steady state, what happens to steady state? d by dt per term is gone. So set d by dt to 0 and assume the force is at large scale, forcing at large scale, a force at very large scale. Okay, so these are assumptions which we made already before. I make the same assumptions. It's the same theory, but it's in real space. Okay, if you make that assumption, then d by dt term is gone. So if you remember, so d by dt is gone. So that was Tu of L plus Fu of L, math cal actually, because this is force times velocity, minus du of L. I am interested in the inertial range which is bigger than the, whose length scale is bigger than the dissipation range. So viscosity is very small scale dissipation range. So go to inertial range which is the intermediate scale. So this term is negligible. Dissipation is effective only at small scales. So this term is gone. So we get, you relate these two with a minus sign. Now what about this FUL? What is it equal to? This is force injection at any position if you look at it. This is equal to energy supply rate, is same at all positions approximately. Now how do I see this? I have argument, but we can write this as, I think I will skip the argument, just look at the proof. I think I do not want to make you more tired. So this is equal to, is constant everywhere approximately, and equal to energy supply rate. So, this is the constant which is epsilon UL, because energy supply rate equal to dissipation rate. So, that means minus Tu must be equal to epsilon U, this equal to 0. So, this must be equal to it, right. So, this is how you connect dissipation rate with the energy nonlinear transfer rate. Now, you can see the proof is almost there. Now, TUL is connected with third order structure function. Now, we can just finish off the proof. So, this is TUL is minus 1/4 of this one, and this was I proved this one I taken already the divergence in spherical polar coordinate. Now, how do I do it? This is just straightforward. So, multiply by, take the 12L square to the left. So, let me do the last bit of algebra now, minus epsilon U 12 L square equal d by dl. Shall I do the integral again, this integral? Integrate the 2 d by dl. So, let us do the first integral. So, this will be L cube by 3. So, I have done this one and this one, these operations. 12 L square went to the left, and d by dl integral is 1 by L d by dl of L 4 S3 of L. So, what is this? This 4, right. Now, the 1 L is sitting here, again take it to the left. So, it becomes minus 4 epsilon U L 4 is d by dl of L 4 S3 of L. Integrate this 4 by 5, right. So, 4 by 5 epsilon U L 5 is L 4 S3 of L, and now divide by L 4. So, this goes and that, okay. So, you can clap. So, this is how we get S3L is minus 4 by 5 epsilon UL. So, I have to say few more words, but if you want to ask some questions, you can do it now.
We are forcing at large scale, but in absolute scale we are forcing why?
So let us see. So I can do it now. So large scale forcing means you are forcing everywhere. So what does it mean, forcing everywhere? So if I take this bucket and stir this stuff, is forcing everywhere in real space. In Fourier space, it is band a small wave number, but it is forced everywhere. So you multiply the velocity everywhere. So large scale velocity versus large scale force, it is affects everything. It's like in the central government, no, something happens, it affects everything in real space. In Fourier space is only the low band. Now if you want the proof, then it's also easy. So let's do quickly. F of L math cal is Fk Fourier. So there is a theorem that in real space correlation is Fourier transform of the spectrum. Now this you have to believe me. So this is a theorem, you can relate. So this is a correlation at 2 points, no, Fu equal to Fourier transform, this is power spectrum, K dot IR. Now this I force at small wave number. So let us say I force at K naught, which is K naught being small. So I put this stuff F K naught equal to F of minus K naught is epsilon by 2. So there are two wave numbers I force, only two wave numbers, not a shell. So this will be epsilon by 2. So this is a constant. So I get e to the power I K naught dot R, fine. And the other guy is also that epsilon by 2 e to the power I minus K naught dot R. Is there a minus K? Sum is only two wave numbers. Sum it up, what is e to I K dot R plus 0 minus K dot R? Is cos K dot R. So cos K naught dot R and epsilon, the half will cancel with 2. Now K naught goes to 0 limit. What is K naught going to 0 limit? cos q naught will be 1. So, this is approximately epsilon u. So, this is how we prove it, okay. But it is kind of physically visible by force at large scale. So, it is going to there is visible at every scale, okay. So, this is how we prove the force field law. Now, just to complete the story, so this is for the third order structure function. Okay, I want to say how to relate this with the spectral theory, our Fourier space theory. So, the connection is the following. Now, remember I had the flux pi u k is connected with the s u u sum over. So, flux of wave number k is giver is inside and receiver is outside, right, this all stuff. Giver mode is inside the wave number sphere and receiver wave is outside wave number sphere, and this is equal to pi u k in the initial range. This is epsilon u. So, what is the connection? So, I write this u squared as a product, dot product of u prime minus u vector. Now, beautifully this is like a mediator, and this is mediator which is connected with that. Mediator is u q. Now, this is product of the same function which is a delta u, no. So, one of them is a giver and one of them is a receiver. Giver, receive, well, so this is giver, sorry, giver, I made a mistake, no, this k, receiver, and this is a mediator. U prime minus u is in fact is mediating, and this is a divergence is coming as this k vector. Of course, this is summing over all. This is in real space I am summing really because all the Fourier modes. So, is implicit that this sum is sitting here. Take divergence, basically you are doing some kind of sum, and this L is connected with 1 by I, L is connected with k, 1 by L is k. So, this is a connection. In fact, it's quite nice that there is a, it must be related and this relation is visible. Okay. Now, this for third order structure function. So, epsilon u is connected with u delta u delta u delta u, this object. What about higher order? So, this has been a puzzle in physics for many in fact 50 years or 60 years. So, we can take the projection along again. So, L cap is along L direction, or in fact is n, this is same as n. Okay. So, take the qth order structure function, SQ is q order. So, delta u to the power q equal to 3 is what Kolmogorov showed, but if q is let us say 4 or 5, what happens? So, it turns out this nobody has even to get a closed form formula from the first principle. Start from Navier-Stokes equation, we cannot get to q not equal to 3, q4 nobody can do it, nobody has been able to do it. Okay. So, this is by dimensional arguments, it is epsilon u L zeta q, this is unknown, and this is called exponent of the structure function. Now, I put average because epsilon u is fluctuating. Okay. What Kolmogorov says is it's kind of averaged epsilon u. So, use epsilon u, and idea is to estimate or obtain zeta q. Now, I will not discuss in this lectures, but zeta q was proven by Shay-Levesque by some assuming that this dissipation rate is fluctuating and it has a log Poisson distribution. Okay. Now, I will not discuss this, but you can look at the original paper. Distribution is Physical Review Letters 1994. Okay. Now, if you make certain assumptions, you find as a function of q. Now, it turns out this fits with the data quite well, but it is not starting from first principle, or you cannot prove it from okay, this is analytically proven. It makes certain assumptions of this distribution of dissipation rate, and it seems to work quite well. Kolmogorov himself had given a theory that the dissipation rates are log normal. So, normal distribution is right, I mean there is a peak. So, normal distribution will be epsilon u. So, this is probability, y axis is, so this one I can explain a bit more, epsilon u. So, it peaks at epsilon u with certain distribution. Had it been Gaussian, it will be on linear scale, it has a certain width. It is not a given number, but it has certain width, right, this Gaussian, like heights of human beings are not same height. This is the average and this is a distribution, it is supposed to be Gaussian. But log normal means if I take the log in the x axis or y axis? X axis, no? So, x axis log epsilon u, then it is normal. So, instead of taking epsilon u, we take log of epsilon u, and it turns out it is Gaussian. Okay. So, that is a log normal distribution, and Kolmogorov argued why it is so, and he postulated that the formula, well, from this zeta q comes of this form, and the data fits okay with mu equal to 0.2. So, mu is a free parameter here. Let us look at how these things fare. Okay, I forgot to say that if Kolmogorov's 5/3 theory, or that S3q is epsilon times L, no? What did I write? S3 of L minus 4/5 epsilon L. So, this is delta u cube. But if I make extrapolation delta u q, what will that be? Just naive extrapolation. So, divide by, so take 1/3 order. So, 1/3, if I just like that, then take q power, the epsilon q by 3, L q by 3. So, zeta q will be q by 3. You got into Kolmogorov's formula, but this makes lot of assumption. If you are averaging, you can't take power in and out, right? You can't do that. I mean, that is not x square average and x4 average. This is not square of this, right? We know this. This you can't say this like that. So, this is not proper. This is only proper for some distribution, but not for all distribution. So, well, we make some assumptions. This is, so this line is q by 3 line, linear line. Shay-Levake is this line. This line. This is Shay-Levake. A log normal, Kolmogorov log normal is this line. The data appears to be closer to this line, but you can see that it deviates very strongly from this q by 3. So, by the time it reaches 10, the difference is around 10%. Okay. So, for q equal to 10, this will be 3.3, but answer is around 2.4 or so. Okay. So, the difference is in experiments. So, these are experimental data and numerical simulation, which Shashwat has also done some of it. So, we can do this data and we find that you are away from the linear line, and this theory is still not done yet. I mean, we do not know how to compute zeta q from some theoretical framework. Okay, so this is what I have to say about structure function. I will stop. Okay, thank you.